Alright, these are the equations that set up tree number 1. And these are what they look like when they're graphed. So we're trying to find the area between the two curves. Now before we can do that, we have to find the points of intersection where they meet. So we set them equal to each other, and we found that they meet at the points x equals plus or minus the square root of 240 over 11. And in decimal form, the original point is a equals negative 4.671 and b equals 4.671. So in order to find the area between two curves, you have to set up an integration. And it's an integration between the two, from the 2 points of intersection. And the top curve in this is y equals negative 1/6 x squared plus 6, while the bottom curve is 1/5 x squared minus 2. Now because an integration finds the area under the curve, you have to find, when you set this up, you have to set the top curve first, and then subtract all of the area underneath the second curve to find the area between the two. Which means our integration is between the 2 points of intersection and starts with negative 1/6 x squared plus 6 minus the quantity of the second equation. Now that we've set up that integration, we have to actually integrate the equations. Now, how we integrated these equations is thankfully the simple way. We use the reverse chain rule, which means going from a second power, we had to go up to a third power and still have the same coefficient. So for example, negative 1/6 x squared became negative 1/18 x cubed, because if you then perform the normal chain rule to get back to where you started, you have negative 3 over 18 x squared, which simplifies down to negative 1/6 x squared. So that means our integrated equation becomes negative 1/18 x cubed plus 6x minus 115 x cubed plus 2x. And then from the 2 points of intersection, so negative 4.671 to 4.671. Alright, so using the fundamental rule of calculus, you have to plug in the upper limit of your integration first for all of the x, and then subtract from that the total quantity of your lower limit plugged into the integration. So that's what we have here. And so the answer generated from this long gross problem will give us the area. So the area, the cross-sectional area of tree number 1 is 49.824 inches squared. Alright, these are the two curves that make up tree number 2, y equals 7 cosine x and y equals x squared minus 3. Now in order to take the integration to find the area between the two curves, we will do the same thing we did before, and we'll set the two curves equal to each other. So they're equal to each other at the when x equals plus or minus 1.623. Now these become the limits of the integration. So to find the area between the two curves, we once again subtract the lower curve from the taller curve to subtract the area below the lower curve from the area below the taller curve. Alright, and so the integration of this becomes 7 sine x minus x cubed over 3 plus 3x. And then we have our two limits here, and then using the second theorem of calculus, we'll plug these two numbers in to find the area. Alright, so when we use the second theorem of calculus, we plugged in the two limits, so 1.623 into the equation, and then we subtract from that the whole equation, but this time plugging negative 1.623, and that gives us the area between the two curves. So the cross-sectional area of the second tree is 20.869 inches squared, which is smaller than tree number 1, so this is the tree we want to give to the knights who say P, because it is more like a shrub.
After passing through the 100-acre wood, solving the problem of the knights who say P, not to mention avoiding a host of other cartoon bears, tigers, piglets, kangaroos, owls, depressed mules, and rabbits, the Knights of Time's Table came to the final leg of their journey.
Oh, who would have thought that the woods could be so filled with lions, tigers, and bears?
Oh my! There are no lions. Didn't you just hear the narrator?
Right, and that depressed mule. Do you suppose he shall ever find his tail?
Not with that attitude he won't. I think, in the name of Miss Hall, look at that bridge!
We're going to have to get to the other side if we're going to continue our most holy quest.
You think I can cross? We're looking for the holy holocaust.
Well, that sucked. Am I in your way? Are you trying to get by? Am I in your way?
I'm with the gentleman with the nasally voice.
Oh, that guy.
Yes.
He wasn't really supposed to cross. See, in order to pass by me, you must answer these questions 3.
That's not fair.
What is your name?
Rose,
What is your favorite color?
Rose,
What is your favorite flower?
Rose.
You can't answer both three times. Get wrong.
That dummy doesn't even look like her.
Hey, it was cheaper than hiring a real stuntman.
It has a pumpkin head.
Oh, just shut up. Did you turn the camera off?
Excuse me, have you seen Rose?
I don't know. Has she been around here lately?
Yeah, I saw her walking down that hill, and I don't know what she went after.
Well, I'm not sure what you're talking about.
Wasn't there someone who was just flying around here?
Why? Do you know Rose at all?
Yeah, vaguely.
No, that was Violet. Sorry. Wrong person.
Well, all right, and I need to get across this bridge.
Well, I can't do that, sir. In order to pass me, you must answer these questions 3. What is your name?
King Arthur.
What is your quest?
To find the Holy Hall Path.
And how far away is Violet's body?
All right, well, let me go ask Rose. I'll be back.
Yeah, good luck with that, yeah.
Alright, considering the guard threw me from a 2,000-foot bridge with a horizontal velocity of 6 meters per second, taking into account the acceleration of gravity, how far from the bottom of the bridge did I fall? Alright, so to find the position of a fallen object, we have to use vectors. Now we have information from 2 different types of vectors given to us in the problem. We know we're taking into account the constant of acceleration when it comes to gravity, which is negative 9.8 meters per second squared. Now that deals with the vertical component of the falling object, so that goes into the y component of the vector. We also know that I was thrown with an initial velocity of 6 meters per second horizontally, so we know the x component of the velocity vector. Now in order to get to the position vector, we have to integrate both the acceleration and the velocity vectors to get to the position vector. So we'll start with the acceleration vector. Now we use the reverse power rule on the negative 9.8 meters per second squared, and we get negative 9.8 t plus c. Now we know that I was thrown with an initial horizontal velocity only, so I have no initial vertical velocity. So when you plug 0 in for negative 9.8 t, into negative 9.8 t, you want to have c equals 0 so that it still equals 0 at the initial point when I was thrown. So we know that our velocity vector is 6 meters per second and for the horizontal component and negative 9.8 t meters per second for the vertical component. Now we have to integrate the velocity vector to get the position vector. So we again use the reverse power rule, and we get 6t plus c for the horizontal component and negative 4.9 t squared plus c for the vertical component. This is where we use the initial position vector to solve for c in both of the components. Now we know that when I was initially thrown, I had no horizontal displacement. So when t equals 0, we have to have c equals 0 so that it still equals 0. And then for the vertical component, we know I started at 2,000 feet. So when we plug 0 in for t because it's the initial position, we have to have c equals 2,000. So our position vector is 6t for the horizontal component and negative 4.9 t squared plus 2,000 for the vertical component. Alright, now that we have the position vector, we can use this to find where the body hits the ground by setting the vertical component equal to 0. So by setting negative 4.9 t squared plus 2000 equal to 0, we can solve for t. Now t equals plus or minus 20.203 seconds. And because time is only moving forward, as far as we're concerned, we're only going to use the positive value. Now, when t equals 20.203 seconds, we can plug this into the horizontal component to find the horizontal displacement. So 6t becomes 6 times 20.203 seconds, and we end up finding that the horizontal displacement is 121.218 meters.
That's how you do math, Rose style.
Alright, so I got this answer from Rose.
But
she's got to be dead.
I'm not dead yet.
Oh, is the answer 121.218 meters?
well, I don't know. That doesn't even look vaguely human. It doesn't even have the same clothes on. The insurance would have been ridiculous with a real stuntman. You're using the same shot for Rose and the Guardian. I don't want to hear it. And turn that camera off. And so Arthur proceeded to meet up with Lancelot to continue to look for the Holy Hall Pass.
Lighting crew? Alright, thank you very much. Alright.
Hey, what?
Was that Rose?
No.
So,
So,
anyway, so, what are you doing here?
well, this commoner and I were trying to discover stuff.
We're not arguing, we're just talking over the complexities of whole mathematics. Which isn't arguing, it's more like discussing.
And so a new narrator was subsequently hired, and the Knights of Time's table came upon a wood.
It looks like we've come upon a wood.
Oh, is that my line?
Yeah. And plus, why'd you guys move on? and so a new narrator was subsequently hired, and the Knights of Time's table came upon a wood.
Looks like we've come upon a wood. Yeah! Wait, what?